Today we'll talk about something called the electric potential, which comes out of electric potential energy that we talked about in the previous lecture, which of course concerns work and energy that were reviewed in the lecture before that. But the electric potential is slightly different than energy. It's actually the energy per unit charge. And we'll talk about what that means, the definition of it, of course, but also sort of the basic idea that it is something which is associated to an electric field all on its own. Then we'll derive the electric potential for a few different cases, for the uniform electric field and for the field of a single point charge, and then show how we can find the electric potential due to multiple point charges. And then we'll do a problem on finding the electric potential for a continuous distribution of charge. And finally, we'll make the connection in the other direction. So if you know the electric potential, then you can find the electric field in very much the same way that if you know the potential energy function, you can find the force from that for a conservative field. So some basic ideas first. In the previous lecture, we found that the change in the electric potential energy as a charge moves through an electric field has a certain equation which depends on finding the work done by the electric force. And so we found that for the uniform electric field, and we found that for the field of a point charge. The electric potential generalizes that sort of in the same way that the electric field is the force per unit charge. The electric potential is the energy per unit charge. So what we do is we find the potential energy of a charge as it moves through an electric field, meaning the change in the potential energy, and we use that as a test charge, and then we just divide off the test charge in the same way that we went from the Coulomb force to the electric field. So the definition of the electric potential difference then is if you have 2 points in space, let's call them A and B, then the difference in electric potential is simply the difference in potential energy as you take a test charge and move it along some path to point B, and then you divide off from that quantity the value of the test charge. So you see that the electric potential will not depend on the test charge itself. Again, the test charge is just a tool that you use to determine the electric potential. And therefore, what it means is that the electric potential depends only on the source of charges that create the electric field, but not the charges that move within that electric field. So that's how we define it. And you'll see on the next page how we do that precisely. Maybe we should expand that definition a little bit to show what it means in terms of the work and therefore in terms of the force and the electric field. So if we use the definition delta V is equal to delta U over Q test, then delta U is minus the work done by the electric force, the electric field on Q test, divided by Q test. Delta U is minus the work, but then I divide by Q test because that's in the definition here for the potential difference. And so that means that we can write minus 1 over Q test times, and we'll use the most basic expression for the work, meaning the most complicated one, which is the electric force on Q test dotted with the dr. And if you remember from last time and the time before that, this is really just symbolic notation. What it really means is you dot together the force with the velocity vector and you integrate over time for some chosen path. But we don't need to think about those details. I just want to show you what it sort of looks like here. But the force, this force that we have, the force of the electric field on a test charge, we have an explicit expression for that. So we can write minus 1 over Q test times the integral over that path of Q test times the electric field dotted with dr. And you see that the Q test cancels out. So what we end up with is that delta V is actually equal to minus the integral over that path of E dot dr. So this shows you explicitly what I was saying above, which is that the potential difference depends only on the electric field. It's basically just another way of talking about the electric field. And in fact, that's sort of the most important thing about it, which is that if you know the potential field, meaning if you know the value of V at every point in space, well, those are just numbers. So you have like V at some point, some position R in space. If you know that at every point in space, then that should be enough information to determine the electric field at every point in space. So if you sort of invert this expression, if the potential difference is the integral of the electric field, well, then the electric field is somehow the derivative of the potential, and it's exactly the same kind of derivative that we saw that related potential energy and force. It is that the electric field vector at every point R is equal to minus the gradient of the scalar field, the potential value at every point R. And that gradient you learn about in Calc 3. It's the vector of partial derivatives. And we'll show how you use it for some simple cases at the end of the lecture today. So, important notes, potential difference depends only on the field, although in order to find it, you might use a test charge to determine what it is. And that's sort of the whole reason that we developed this notion of a potential, is so that we can determine the potential in space and then directly from that find the electric field. So you can think about it as we had to do problems where we used a charge distribution to find the electric field vector at every point in space, and that was a little bit of a difficult problem because you had to find each component of the vector. Well, now what we're going to be able to do is look at a charge distribution and find the potential value at every point in space, which is just one number, and then from those values you can determine the electric field vectors directly, and we'll show how to do that. If we have a uniform electric field, then we could calculate the potential energy difference as you move a test charge through there. And I think I didn't actually do that in the previous lecture on potential energy, electric potential energy. So let's do that now. So let's say that this is point A, and I have a test charge that I place in the field, and then I move it to some other point in the field, which I'll call point B. And I could take some sort of arbitrary path, like this. Call that some path C. But it'll turn out that it's easier to make a calculation if I choose a very specific path to calculate that potential energy difference. So let's write down the equations first, and let's write down the equation. So first we'll calculate the potential energy difference, and then we'll use the equation for the electric potential to find that. So potential energy difference, remember, is just minus the work done by the force of the electric field, and you could say on Q test, from point A to point B. And whenever you see that you have to calculate a work, you have to go back and remember that there are different expressions that you could use. There's that most general expression, which is sort of complicated, but then in the case where the force is constant, then you can use a very simple expression. And in fact, in this case, we have exactly that, because remember the force is just Q times E, but E is uniform, meaning that it's the same everywhere. So we can use that very simple expression. Now, if we try to do it over this, it might get annoying to try and calculate it. So instead, let's choose another path. And I'm able to do that because we know that the electric force is a conservative force. So the work done between point A and B is the same no matter which path I choose. So if I choose this path, where I go perpendicular to the field lines there and then parallel to the field lines here, so we could call that like path 1 and path 2, then it should be a little bit easier of a calculation. So let's write that out. So it's going to be, well, first we'll just call it minus the work done on path 1 by the electric force plus the work done on path 2. And as we said, because the force is constant over these paths, then we can use the very simplest expression for work, which is that it is the force of the electric field dotted together with the displacement. So the displacement over path 1 times the force of the electric field dotted together with the displacement over path 2. So let's look at what those are. So if we have the test charge, and let's say it's here, well, the electric force is going to be, let's assume it's a positive test charge. So then the electric force will point in this direction. And the displacement vector over that part of the path will point here. So this is delta R1. And what you see is that the electric force dotted together with delta R1 well, that has a 90-degree angle between them, so that means that this expression is 0. The dot product of perpendicular vectors is 0. In the second case, let's take a look. Let's give ourselves a coordinate system to work with. And let's say that the electric field is pointing in the positive x direction. So it's a uniform field, which means I can choose an axis to point in the direction of the field at every point in space. And so if I use that, then what I find is, looking at the test charge at a point here, I see I have the force of the electric field pointing with the electric field, and then my displacement vector also points in the same direction, delta R2. So those things have a 0 angle between them, so we get the magnitude of the electric force times the magnitude of delta R2 times 1, the cosine of 0. That becomes minus the absolute value of Q test times the magnitude of the electric field times delta x here. And it turns out that the expression could actually just be written as minus Q test magnitude E delta x. Meaning, if I go, if I have a delta x which is positive, I go in the direction of the electric field, then I get a negative value for the potential energy difference. And if I have a delta x which is negative, meaning if I go opposite to the field lines, then I'll have a positive potential energy difference. And that should make sense based on our ideas about work. Remember, if you lift up an apple, then the force of gravity is pointing down on that apple, and you're lifting it up so the displacement is up, so the work done by gravity on the apple is negative, but since the potential energy difference is the opposite of the work, the potential energy change of that apple is positive with respect to gravity. So it's the same idea here. If you move a test charge along the field lines, then you're moving that test charge in the same direction as the force, meaning the work done by the electric field is positive. But since the potential energy difference is minus the work, then you have a negative potential energy difference. Another way of thinking about it is if you let go of a test charge, it will fall in the direction of the force, and that potential energy will go down. So this is our expression for the potential energy of some charge in a uniform electric field, which I don't think I did in the previous lecture. So what is the potential difference? Well, the potential difference we defined to be delta U divided by Q test. So this is simply going to be minus the electric field magnitude times delta X. And that's the potential energy difference between any 2 points. You could also then choose a particular point where V is equal to 0. So we could say that that's just the origin of our coordinate system, and then we could write that the potential as a function of x is equal to minus Ex. So that's what we call the potential function. So anywhere in space, given this coordinate system, V can be written as minus the field magnitude times the value of x. And then the potential difference will come out to be exactly this. That process of choosing a 0 point for the potential is exactly the same as what we saw for choosing a 0 point for the potential energy in going from a delta U to just a U function. And we'll do that in each of these examples. So what about the field of a point charge? Well, I won't go through the entire derivation of the potential energy again, but let me just remind you of the setup so that you remember what it looks like. We have some Q, big Q, which we might in this case call the source charge, and it will create an electric field. So let's say it's a positive charge. So it has some electric field in space that looks like this. And then you could move another charge in its field. So in this case, we're going to talk about that other charge being a test charge. In the previous lecture, we just talked about some little q, whatever it is. You move it from one point in space to another, and you get a difference, a potential energy difference. So if this is point A and this is point B, then you get some potential energy difference in moving it from one point in the field of the larger charge to the other. And we found the expression for that. It was this here. So we had to do an integral. Remember that we chose that our path went straight outward and then along the circle here, and it turned out that we only really needed to calculate the work along this path here, and we came up with this expression. Now we can immediately write down what the potential difference is. So the potential difference due to a source charge Q is going to be equal to delta U Q test divided by Q test. So what does that turn out to be? Well, that's just K, Q, the Q test cancels, 1 over RB minus 1 over RA. And this RB and RA, they just mean the distance from the capital Q to the point that you're talking about. So that's RA and this is RB. So we have an expression for the potential difference moving in the field of a point charge, and we could then make that choice about a place where the potential is going to be 0, and we'll make the same choice that we did for potential energy. So we'll say that choose, and it's important to remember that it's just your choice. You could make a different one, but I'm going to give you the one that is sort of the standard choice. Choose that V at infinity is equal to 0, meaning that the potential as you get infinitely far away from the source charge will be called 0. And then that will set the values of V at all other points in space. So what we'll do is we'll say, okay, let's let our initial, RA, be equal to infinity, and RB be equal to just some R value. So what do we get? We get VQ at final minus initial. So final minus VQ at infinity is equal to KQ times 1 over final, which we said we'll call R, minus 1 over initial, which we said we'll call infinity. And then we use what we decided. We decided that this should be 0. It's not naturally 0 in any way, it's just our choice. This one is naturally 0. 1 over infinity is always 0. And therefore we get to an expression for the potential for a point charge. Let me give myself just a little bit more space. And the expression for the potential of a point charge is VQ at a distance r from that charge is equal to KQ over R. There it is. So that's the potential of one single source charge. And you notice in the end, of course, it doesn't depend on the test charge. It's really just an expression for the electric field of that source charge. It only depends on capital Q. And now we can use that. So we can use that to talk about the potential due to multiple charges. And the potential due to multiple charges will just be the sum of the potential that you get at a position in space due to each of them. And then, of course, you can extend that to the potential of continuous charge distributions by chunking it up and treating them as point charges, exactly as we've done for finding total charge, finding the electric field, etc. So let's do just a quick example of multiple charges. So maybe let's say that we have a square of side L, and let's say that we have 3 charges, maybe Q, Q, and Q. They're all the same. Let's say that they're positive. And then this distance is L. So the question, what is V at point P? So what is the potential at point P? And the answer to that question is that V at point P is equal to the V due to Q1 at P plus the V due to Q2 at P, and let's call these Q1, Q2, Q3. Q3 is equal to Q, which is positive, plus the V of Q3 at point P. So what are those things? Well, we just use our equation. So we have, for the first case, we have a distance to the point, R1, which is going to be equal to, well, R1 squared is L squared plus L squared. So this will be the square root of 2L. So we have for our equation, K Q1 over square root of 2L. Remember, the equation for V at a distance R from the source is KQ over R. So that's the V for a single point charge. So we've applied that to our first charge. Now we move on to our second charge. So that is going to be KQ2 over R2, which is just L. And then finally we have exactly the same thing for the other one because it's exactly the same distance away. So it's KQ3 over L. And because all the Q's I said are the same, we have, we have KQ over square root 2L plus 2KQ over L. And you could simplify if you want to. I don't think I'll do that right now. But you see the basic idea. If you want to find the potential at a point in space, then you have to look at all of the source charges and calculate their potential at that point in space, and then you just add them up together. And that's the value of the potential. So let's do that in a more complicated situation then. Let's look at the continuous charge distribution producing an electric potential at a certain point in space. And let's do a long, thin rod. So let's actually take a rod that has finite length to begin with, and then we'll let the length go to infinity from there. So we can choose a coordinate system, maybe place a point on the x-axis, here. And maybe I'll just say that point is a distance x from the rod. And we want to find the potential at that point, and we're going to do it by assuming that the rod can be broken up into chunks. And consider one little chunk, so maybe Qn here. Qn has delta y, let's say, for its length. And then let's continue to draw the picture a little bit. Oops. So there's an Rn, the distance from that charge chunk to the point in space that I'm interested in. The position of that chunk, if this is chunk Qn, its position is called Yn. And so I think we're ready to evaluate this now. So we're looking at the potential at point P, and we say that it's approximately equal to the sum, where n goes from 1 to capital N, of the potential due to each chunk. So let's say VQN. So meaning the potential of a point charge, which is the point charge Qn. Remember, small steps. Then we can use the equation for a point charge. So that's going to be K Qn over Rn. And now you know where we're going here. We want to try and come up with an integral. And in order to get an integral, we have to have a Riemann sum. And you can see already sort of where that sum will be. It's going to be a sum over the y-axis, which means we're eventually going to have an integral over the y-axis. And in order to get that into an integral, we need two things in our Riemann sum. One is we need the y value, yn, and the other is we need delta y. So we need to somehow get those two things into this expression. And they are there because we can say, well, this rod has a linear charge density. So this is the charge per unit length. And that means that Qn will be equal to lambda times delta y. So let's plug that in. So we have K times lambda delta y now. And then Rn is not the variable that we want to integrate over. We want to get Yn. So then we'll have to use this triangle where we have Rn, x, and Yn. And that means we can express Rn as the square root of Yn squared plus x squared 1/2. And that's a Riemann sum. So you see that you have a delta y there, and you have this expression there in the which has Yn. And therefore, if these were approximately expressions, then Vp will be the integral from, let's say, from minus L over 2 to L over 2 of K lambda over y squared plus x squared to the 1/2 dy. So that's the expression for the potential at that point. Remember, when we did this with the electric field, we had to do two things. We had to find the electric field vector, so we had to find the x component and the y component of it. In this case, we just have to do a single integral to find the potential, and then we could use that to find the electric field by taking a derivative, as we'll talk about in the end. So the potential sort of simplifies the work. You only have to do one calculation because it's a scalar quantity. Find the potential at one point in space. I'm not going to do the integral because I don't know how to do the integral, so you'll have to look it up and figure it out. Now let's talk about this last issue of going from electric potential to electric field, and we'll do it for a couple different cases. So remember the basic idea. The definition of the electric field given a potential is that it's equal to minus the gradient of the potential function. And maybe I should make this a little bit more specific, which is to say that I'm looking for the electric field vector at a point in space, position r, and I take the gradient of the potential function, which is a scalar value at every point in space there. So you see that these are fields here. We call this a scalar field because for every position r that you go to, you get back a number, v, and this is a vector field because for every position r you go to, you get back a vector, the electric field vector. And the connection between them is that you take the gradient of the scalar field to get back the electric field. And that gradient, it means in math, I hat times partial x plus j hat times partial y plus k hat times partial z. So we won't do anything as complicated as this sort of derivative in this class, but we can look at some special cases which are, for example, one-dimensional. So let's look at those. So example 1, uniform electric field. Well, we found that the potential function as a function of x was equal to minus magnitude of the electric field times x. So remember, x points along E. That was what we found on that very first example that we did. Okay, so if we look at this expression here, well, it only depends on x, so derivatives with respect to y and z will go away, so we only have the ddx. So our expression then is going to involve only the x component of the field. So E sub x is going to be equal to the derivative of v, and that's just a regular derivative. That was really terrible. So it's minus the derivative of v with respect to x. So what is that? Well, it's just minus e. And the rest of the equation, the derivatives with respect to y and z, well, those will both go to 0. So the j component, the k component, well, we can just write down ey is equal to ez is equal to 0. And something's wrong here. Why did I? Oh, because I screwed up the equation. So let's, as I always say, go slowly. So this is going to be, e sub x is going to be, it's going to be minus the derivative of x with respect to of v of x. So that's minus the derivative of x with respect to x of minus ex. And then that whole thing then becomes plus e. That makes more sense. So now, remember, we have the electric field pointing like this. We have the electric field obviously points in the direction of the arrows, so that means its x component, if we choose the x direction to be in the direction of the electric field, should just be positive e. One other thing we should mention about this, which I don't think I said earlier, is that just by looking at the electric field and using this expression, you can see where the high potential region is and where the low potential region is. So as you see from this expression, as you increase x, meaning as you go along the field line, v gets more and more negative. So v goes down. So we can just write here, this is sort of a nice picture to remember, that the top of the field lines, the back end of the field lines, is the high v area, and down on the field lines is the low v area. So you can always state that about the potential in a uniform electric field. Final example, let's do the point charge. electric field of a point charge. And we found that V for a point charge is equal to kq over r. The expression for the gradient is a little bit complicated if you start to talk about spherical coordinates, but we're only interested in the first part of it, which would be ddr. So along the r direction, you have a ddr in the gradient. So it'll turn out that you can just write the r component of the electric field is equal to minus ddr of VQ. So what is that? Well, it's minus ddr of kq over r. And that thing becomes, well, the derivative of 1 over r is minus 1 over r squared. So you get minus plus kq over r squared. So we find that the radial component of the electric field for a point charge is equal to kq over r squared, meaning that it points outward for a positive q, and of course inward if q is negative. Okay, that ends this lecture.